Swayam Prabha. Digital India. Educated India.
Very good afternoon to all of you. Today we are going to have fluid kinematics, solving some of the problems on the blackboard. Looking at, as I said it earlier, we are again having same reference books starting from Sinjal Simbala, F.M. White and Vidyasagar Fani. So my sincere request to you to please look for the book of Sinjal Simbala book, which gives a lot of illustrations to visualize the fluid flow problems, because if you try to understand the fluid kinematics, which is a very interesting subject, besides this solving the problems also we should look at how the flow behavior, flow visualization technique, that's what very good illustrations are there in Sinjal Simbala book. So please refer to Sinjal Simbala book of fluid mechanics and other two books as we refer earlier case also. Looking that again I will show it, there could be conduct a very small experiments which is called Hellis apparatus. So where we can have a apparatus like this and you can create the streamline pattern, the stick line pattern and path line patterns using this the small device which is called the Hellis apparatus. Like for examples, if you can look at that, if I have the obstruction structures like this and having the flow patterns like this, you can see the streamline patterns, what is going on near the structures and far away from the structures. So very easy to visualize the flow when you use the apparatus like Hellis apparatus. And if you look at very interesting flow visualizations are available in internet. Please refer to look at these flow visualizations data, videos which are available in the internet. Like for example here it's showing it how the wake formations happens just behind of the cylinders when uniform flow is going on, and how the wake formations happens is a very interesting phenomenon. Similar way you can have the oscillating plate, and because of the oscillating plate how the streamline patterns are changing with respect to the time, the path line, the streaks line, all you can visualize using this type of video. So my sincere suggestions to you, please visualize the flow visualizations by visiting the YouTube sites. You can see that how the flow patterns are changing it. This is what the examples what earlier also we showed to you, that if you have a triangular structures and how the wet vortex shadings are happening it, and it's quite interesting way if you see these unsteady patterns of wet vortex pattern. These are data obtained from the CFD solutions. So we can get it from the CFD solutions, these type of vortex patterns, and very interesting vortex patterns, and that's what it shows that how the average velocity line changes with that and with a comparisons with the experimental data. So what I am to say that if you look at this advanced level of flow visualization technique and the experiment techniques what is available today, we can have very interesting flow problems. We can get the solutions, we can visualize the streamline, streaks line, the pressure distributions, the velocity distributions, the acceleration distributions, all field we can see it. So with having these introductions levels, let us solve the 6 problems on the blackboard. Before starting solving the blackboard applications, let me just have a recap that what we already discussed in the fluid kinematics is that you know that any velocity field we can define as three scalar components. The scalar component can have the velocity scalar component can have the positions and the time, the independent part. That's what the velocity distribution. Similar way, the rate of the change of the velocity is accelerations, but in terms of local accelerations and convective part, we can define the acceleration terms. Similar way, when you have a motion of the fluid particles can have four type of conditions, the motion and deformations like translations, rotations, linear strain and the shear strains. We discussed more detail in the last class. So here I am just doing the recap for you to just look at this is the velocity distributions, the accelerations field, and there could be the translations, rotations and the deformations like linear and shear strain. And if you look at, if you have the rotations, we can write the rotations quantity in terms of the velocity field. Similar way, the shear strain components also we can write in terms of the velocity gradients. And we have the vorticity measures, what we derive in very details, we can compute the what could be the vorticity in different cases. Look at that, when you have the flow is incompressible flow, that means when you have a volumetric strain is equal to 0, the delta dot product of the free velocity should equal to 0. These are the equations we are going to use more detail when you try to solve these simple problems what we are going to address on the blackboards. So the basically these are the recap, the basic equations what we are going to use to solve the problems on the blackboard. Let us start the first example 1. The example 1 says that what is the irrotational velocity field associated with the potential functions as given here. We have to find out the irrotational velocity field. Does this flow field satisfy incompressible continuity equations? So it has two steps. The first steps we have to find out what is the irrotational velocity field. So that's the points. The already is given the flow is irrotational. Flow is irrotational. So that's the condition is given. That means for these velocity potential functions, which is the functions of, if I write it, is a function of x, y, z and the t. The velocity potential function is the functions of the positions x, y, z and the t, if you can see these independent variables. So if you have the velocity potential functions which is function of x, y, z, t, let me I just give a simple examples. If I have the velocity potential function is a only one space functions and another time functions, and if I plot these the functions could variables like this, which is a functions of x and the t, and to determine what could be the velocity as the velocity potential function satisfy for this flow field, we know from the definitions that the u will be a partial derivative of velocity potential functions and the v will be the partial derivative functions with respect to the y directions. So these are the scalar component of v, u and the v, the velocity functions what we can get it. So that means if you look at the graphically, what it indicates is that when you try to find out the velocity, that means from the partial derivative directions, the phi changes only the x directions when you don't consider other component. That's what's of the negative of that's what indicate for us the velocity field. So, looking that definitions, let's come back to the problems which are quite easy problem for us to solve here. That as we know it, the u is the partial derivative of the phi with respect to x with the negative signs, because it's opposite directions of that. Similar way, the phi will have the negative signs of this. If I substitute that value, that means if I just compute it, what could be the partial derivative of phi with respect to x, you can look it, except these two terms, I don't have an x term here. So, those terms becomes 0. So, if you look it that way, if you do a partial derivative of this, I will get it minus 6x plus 3. Same way, if I compute it, the scalar velocity field in the y directions, which will be the partial derivative of with respect to the y. If you look at these equations again, what we can see it in these equations, only the y is in this term. So, others can be considered as a constants. So, if you look at that and do a partial derivative of phi with respect to the y, you will get minus 6y. So, these are two velocity field which we obtain from this case. Now, if you look at these are the velocity field, that is what is the part number A, what we are looking for, irrotational field. Now, the second part of the problem, does the flow field satisfy the incompressible continuity equations? Since the flow field what we are looking in a two-dimensional, the continuity equations for two-dimensional flow field will have del u by del x, del v by del y is equal to 0. So, it is quite interesting to look at that. That means we can again do a partial derivative with respect to y x. This is what also partial derivative with respect to y, and substitute it. If it satisfied it, then we can say it satisfies the continuity equations. So, if you look in this part, if you do y del y del x, then we will get it minus 6. Similar way, del v by del y will also get minus 6. So, substituting this value, what will get it? Minus 6 is minus 12. That means it is not satisfied. That is what is the answer for the second part. Okay, let us solve the next example 2, in which the stream function is described as the psi functions. The stream function is defined as the functions of SQ minus 3x y square. Determine the flow, whether the flow is rotational or irrotational. If the flow is irrotational, then indicate the correct value of velocity potentials. So, the first part of the problem is that we have to prove whether the flow is irrotational or rotational. If I try to explain you that now we have the stream functions, which is functions of only the two-dimensional x and y. That is what could be a representing like a stream functions like this, and we try to find out whether the flow is rotational or irrotational. The questions comes is that to find out whether the flow is rotational or irrotational. What do we mean by that? That means we have to compute it, the vorticity. If this vorticity becomes 0, that means we can say the flow is irrotational. So, we have to find out the vorticity factor. We have to find out the vorticity factor. In this case, it is only the 2 dimensionals. We need to have compute the vorticity factor in z directions. Okay, that means we need a vorticity factors of z direction components. If that becomes 0, then that what indicate is the flow is irrotational. That's the what. If not, the flow is rotational. Let us compute the vorticity factors. The mathematically, as we define it, mathematically we define the vorticity factors, vorticity factor as in the z directions is a functions of so it's a partial derivative of v scalar component with respect to y, scalar component of y u with respect to y. This is the vorticity factors component in the z direction. So, we are just looking it in the z direction vector vorticity components and only z directions. Now, the problem is very simple, is that we will do a partial derivative of the stream functions to compute it what will be the v and u. Once you know that, we can compute it what will be the vorticity factors. What is the relationship between the stream functions and the velocity scalar velocity components? As y definitions what we know it, the velocity component of u will be the partial derivative with respect to y directions. If you look at this u components will have the partial derivative of stream functions y directions, that what is given the scalar component in x directions, and the v is given is the partial derivative in x directions. The negative of that is represent the v component. That means the scalar component in the y directions. By substituting this value of the stream functions, we can get it. This is what minus 6y, and this is what minus of 3s square and 3y square. That's what will come out to be minus 3s square minus y square. Now, as I know this u and the v component, I will just substitute here to compute it what is the vorticity factor in the z direction. This is very simple. Once I know the scalar component of u and v, which is a function of the partial derivative of the stream functions, once I get that things, that what I can substitute here to compute it. That's what you can compute, do a partial derivatives where we are not going a step by steps, but what you will get it minus 6x minus of minus 6x, that's equal to 0. That's what indicates is flow is irrotational. That means that's what is the first part of the component, is that we have proved that the flow is irrotational. as the verticity factors becomes 0. That the first components. So, the second part of the component is that if the velocity potential functions is given to us, okay, the velocity potential function is given to us. In this case, we have yq minus 3x y square to find out whether this is what also indicate it is a flow is irrotational. That means the condition is irrotational flow conditions. That's what also we can get it. The basic equations is for flow irrotational is the Laplace equations with respect to the velocity potential functions. That means as it's a equal to 0. This is the Laplace functions with respect to the phi in the two-dimensional form, the x and the y components. So, that is what is indicating for us to substitute this the phi value and try to look it, does it satisfy is equal to 0. If it is equal to 0, then flow is irrotational. When I substitute this value, that means we compute the first components is that the which is, if you just split like this, you can easily find out what could be the values. Like for examples, if you put it this function 3yq minus 3xy square, if I do a first partial derivative, this 3y square will come in. So, if you look at this first second partial derivative of phi with respect to x, we can split like this, and looking these terms, you can find out the first partial derivative will give us minus 3y square. And second one, if I do it which does not have a function of x, then definitely it will give us the 0 value. The same way, if I compute the partial derivatives of the with respect to y, that is what will give me 6y minus 6x. So, if I substitute these values, the Laplace equations of phi s square here, that what will get it 6y minus 6x. So, it is not equal to 0. That means the flow is rotational. Flow is the rotational, and it does not satisfy the basic equations of the Laplace equation, which is a continuity equation of for the flow field. The similar way, if I go for the second components where the another phi function is given, phi is minus 3s square y. So, we have to again just change the functions, find out whether it satisfies the Laplace equations of the phi value. If it satisfies with the Laplace equations phi value, then we can say that this is what the velocity potential functions for this flow process. If I substitute these ones again, like the compute the partial derivative of phi with x in a second partial derivative of phi with respect to x, that what will give us if I substitute these values, that's what will give is for here is minus 6y. Similar way, if I look it, since it's only the first order y is there, I can easily say it. This what will becomes 0. So, if you look at these two terms, minus 6y and 0, definitely the Laplace equations, after substituting this Laplace equations, that what will be equal to 0. So, it's not satisfied. This is what very simple examples just to look it by substituting this the velocity potential function. Does it satisfy the Laplace equations? If satisfy the Laplace equations, that means it's a velocity potential field. If not, then it is not a appropriate velocity field to define this flow of behaviors. So that what we have to look it for this case. Let us solve the third examples, which is a very interesting problems. The flow through converging nodules as given in the figure can be approximated as one-dimensional flow. A velocity distributions y equal to yx, and from the nodule shown in this figure, and assume the velocity varies linearly at this point is b naught, and at the entrance points, and the velocity at the exit point will be the 3 times of v naught, and the velocity distributions is given with respect to the x directions. This is the what the nodules. The velocity field is given as the ux is equal to v naught 1 plus 2x by L. This is what the velocity distributions given to us. What we have to need to compute it, what is the accelerations in the x directions du by dt, that du by dt at the entrance point at this x equal to 0, that is what the entrance, and this is what of exit of the flow. So, if this is the conditions, we need to compute it, what will be the accelerations ax dy by dt if the v naught is the numerical value of v naught is given as the 10 feet for second, and L the length is 1 feet. Now, if you look at these problems, it's very easy problems. It maybe has described as the converging nodules giving the velocity, increase of the velocity as the nodal dimensions coming, decreasing trend. But in mathematically, it's a very easy that we are defining it what could be the accelerations as the total derivative of u component with respect to the time. And as given in the figure, also I am just highlighting it. This is the what one-dimensional flow, only x directions, only x directions component what we have. That means the y definitions, the accelerations and along the x directions, the accelerations in the x directions can be written as very simple form. It's just taking the definitions that the accelerations will be total derivative of dy dt. That's what will represent as a partial derivative of time, the local accelerations component, and convective accelerations component in the x directions. That's what we are looking at. But if you look at these problems, what are the components can be neglected? As it's a steady flow, there is no time component. On this, we can make it this is equal to 0. And since it is a one-dimensional flow, as it's a steady flow, there is no time component in the velocity field, and it's a one-dimensional flow, these the components also becomes 0 as it is one-dimensional flow field. That's what also we, these components all becomes 0. So it's quite easy, we have to compute this part. So if you just substitute this value and do a partial derivative of this u with respect to x, and if you substitute it, we will get it the du dot by substituting this dy dt, I will get it this value, that 2 v naught square by L 1 plus 2x by L. Okay, so it's very easy, as you do a partial derivative with respect to x. If you do the partial derivative, you can look at what will come it, v naught by 2 by L, and substituting this the u value, you will get this value. So we know this, how this accelerations x varies with respect to x, and what is the functions in terms of v naught and the L. So we have to find out what will be the velocity when x equal to 0 and x equal to L, and the v naught is given to us. So the given data, using given data, we can compute it, the accelerations in the x directions dy dt at x equal to 0. I am not just substituting here when dy dt x equal to 0 value, substituting the v naught and the L value, that's what we will get it, 200 feet for square. The same way at exit point where x equal to the L, just substituting here x equal to the L value, we'll get it, the du by dt is equal to 600 feet for second square, which is given is 3 times of v naught. So if you look at that, we can compute this, the velocity is increasing, the accelerations also increasing in that point. That's what we are computing using that substitutive value. So let me summarize these problems. One of the easy problems, only it has described the velocity field, giving a converging nozzles and telling this the velocity at this point is equal to v naught, and the velocity increases into 3 times of v naught here, and the velocity was described here, and that's what we are just substituting as computing the acceleration in the x directions only. That's what we just substitute mathematically, get it this value, what will be the acceleration at the entrance point and the exit point. This is one of the easiest problems. So let us come to the example 4, which is indicates that a simple 2-dimensional flow, as shown in this figure, it's a 2-dimensional figure flow patterns. The upper boundary is being a rectangular hyperbola, is given a equations is equal to xy equal to the k, this upper part as given it that, and assuming the scalar component of velocity fields are as given as the Vx is equal to minus Ax, Vy is equal to Ay, and the Vz is equal to 0 as a two-dimensional field, and where the A is a constant. A is a constant. We have to determine the streamline pattern and also find the acceleration field. The problems what we are looking at, we have to determine now the streamline, the patterns means we are looking at what could be the equations for that, and also we are looking at what will be the accelerations field. These two the problems, which is a very straightforward equation, looking at that as we have given the velocity scalar components, we have to find out the stream functions. Once you know the stream functions, then we can derive what could be the accelerations field. That means you can sketch each the stream functions could be like this, will come it as expanding it. So we can draw a streamlines like this. So we are looking at what is these functions. So defining these stream functions. Now if you look at the result part, what we are looking at here, that we need to put the basic equations of the streamline equations. Okay, the definitions are the equations of the streamlines as the y definitions. What we know it that dy by dx f of a streamline, that should be equal to by bx. This is what the definitions. As you know it, when you take a tangential component of a streamlines, that should be indicate you the velocity vectors. This is what the velocity vectors at this point and the tangential component are the parallel. That's what the definitions of the streamlines. So we are defining that definitions in mathematically. The slope of the streamline is equal to Vy by Vx. So if I substitute this Vy by Vx, you can just substituting these values, we can get minus y by x. Minus y by x. So as we are looking at what could be the streamline functions, this is what let me size a streamline functions here. See, if I do a integrations, the integrating the above equations, we get that the value, or we can write it very simple form is the xy equal to the c. That means again it's indicating it also will have a hyperbolic nature of the streamline functions. That's what is define the boundary, the rectangular hyperbola functions where it is following for the streamline functions. That's what we are getting from this is the equations for streamline. Now if you look at to compute the accelerations components. So basically we look at two accelerations component, as there is no the time components, we can, as the flow is steady, which is very easy to compute now, we can compute x values as given earlier dy by dt, total derivative of y with respect to time, that's what will become it, del u by del x u So if you just substitute, as in this case, this is what the u, as this is the v components. So these components becomes 0. So you know its value to that, but it doesn't have a functions of y and z. So these components 0 and these components 0. So substituting this value, will get its value is equal to a square x. Similar way, we can compute ay, which is dv by dt. Writing the same expressions, instead of u, we can write the scalar component in the y direction is v, and if I substitute it, I will get it a square by y. That means the accelerations becomes a is the accelerations field in the two dimensionals. That what will be the a square x I a square y j component. That's what the answer for this problem. Let us solve the next examples. That is example number 5. An incompressible flow around a circular cylinder of radius a, as given in the figure, is represented by a stream functions as given it here is u r sin theta plus u a square sin theta by r. R is the radius as a variables, and the total radius of the cylinders is equal to the a. A is a radius of this, and the u is here represent as the free stream velocity. Free stream velocity. So we need to compute it. First we have to prove it. The Vr, the radial velocities is equal to 0 along the circles when r equal to y. So we have to first find out the radial velocity Vr, is it equal to 0 when r is equal to a value, and the tangential v theta component. Also we have to find out the value of theta, find out the value of the theta where the magnitudes of the velocity factors should equal to the free stream velocity components. So it's bit analytical way to compute it, but if you look at the stream function is given to us, we have to compute the radial velocity and the tangential velocity. So the problem is very easy, but only the problem is here it has given in terms of cylindrical coordinate system. Cylindrical coordinate systems. So we have cylindrical coordinate systems, that's what we are using it. So we have to write this, the velocity, the function in terms of the stream function for a cylindrical coordinate systems, as the flow is also the flow is incompressible. Okay, that's the basic definitions here. So in cylindrical coordinates or the polar coordinate systems, we can define it, the velocity field, we can define the velocity scalar component as given like this, that BR will be 1 by R psi theta, and B theta will be minus R. So, please refer to a books to know what is the definitions of the relationship between velocity scalar components and the stream functions for a polar coordinate system, which is very same way what we do for that, but just if you look at the one R components where it comes when you have partial derivative with respect to theta values. So, as this problems is given to us, we have just to find out whether the VR, the velocity, radial velocity component, is equal to 0. So, it is a very easy things. Now, let us compute it by getting substituting the phi functions. You can compute it. That means I am substituting the stream functions as given it here. Is u r sin theta plus u s square sin theta by r. So, if you substitute but do a partial derivative with respect to theta and put it this value, which only comes out to be minus u cos theta 1 minus a square by r square. If you look at these functions, when the r becomes a, no doubt the V's will be 0. Look at this function. If you substitute a equal to the r, these components become 0. So, Vr will be 0. That is what is the first component what we proved it. Now, looking for the second component, that what will be the value of B theta. That means with respect to r. Just substituting these stream functions, partial derivative with r and negative of that, which indicates the tangential velocity component along at the theta locations. That what will come it here is u sin theta plus 1 plus a square by r square. So, when you have a becomes r, that means the conditions when a is equal to the r value. So, you will get is v theta will be the 2 sin theta b. That is the tangential velocity. So, r equal to a, the radial velocity is 0, but the tangential velocity is equal to 2 times of v sin theta. Now, we are looking at what theta values we will have the resultants of the velocity vector is equal to the free stream's velocity. This is quite easy for us. That means we can, as you know this Br and B theta value, we can find out total magnitudes of the velocity vectors, and that what will equate to the 0, and that the conditions at which theta value it gives a value equal to the resultant velocity is magnitudes equal to the, this is the conditions what we are looking at. If I just, as I know it V and B theta, and I can get the magnitudes, and if I equate with a u value, I will get it, the sin theta should equal to the plus minus half. That is what indicate for me theta could be 30 degree, 150 degree, 210 degrees and 330 degrees. So, you can look at that you will have a theta equal to 30 degrees. After that, 150 degree, 210 and 330 degrees, you will have the magnitudes of your resultant velocities is you will be equal to the pre-stream's velocity, which is very interesting. The figures what you can see on the blackboard. A two-dimensional dipole source at the origins produces a steady incompressible flow with a stream functions as it's given. The stream functions is given to us. We have to find out the directions of motion of the fluid particles at the x equal to 6 and y equal to 9. The x equal to 6, y equal to 9, we need to know it what could be the directions of the fluid particles. Okay, directions of the fluid particles. So if you look at that, that means if it is a dipoles and the streamlines could be like these functions as you look at these function behaviors, that means at a particular locations we are looking at what could be the flow directions. Okay, what could be the flow directions. That means we have to find out if a streamlines are going through these, what could be the functions of the streamline with respect to y and x, the slope components. If I know the slope component of that functions at that point, that's what will give us the directions. So the first, let's go for we as you know it, the along the streamlines. Okay, the d phi is equal to 0 because along the streamline the stream function's value is constant, it doesn't vary it. So d phi y equal to 0. That's what is indicate for us. If I substitute the d phi equal to 0 for this case, I'll get it the d phi equal to 0. That's what indicate for me the s square y square dy y 2x dx 2y dy divided by s square plus y square square root. That's what is equal to 0. That's what is equal to 0. So here we have for a very basic, if a phi is a function of x and y, the total derivative of that, that's what we can expand it and substitute for that, you can get it, these components. Okay. Just you follow any mathematics books to know it, how it is expressions is coming it. If I rearrange this term, then I can just rearrangement of the terms, we can get it dy by dx is equal to, just rearranging these terms, we can get it 2xy divided by x square minus y square, and I just substitute the value of x and y. As I substitute these values, it will come with minus 2.4. So dy by dx is this. That means we can find out the tan inverse of these ones of 2.4, which will gives us the value is will come it will be minus 2.4. That's what will go give us minus 63.4 degree. So it's giving it that when you have a x and a y value, the velocity vectors will have a angle minus of 67.4, where you can find out what will be the directions. Now the second components we are showing it that what could be the the sketching of the streamlines. The sketching of the streamlines, if you can find out that if you look at the streamline functions, and since it's a dipole, that means there is a two source components are there. There is a two source components are there, and we are drawing the streamlines patterns like this. So it is should be rewritten into the functions in terms of a circular equations. So considering that part, what we define it that the streamlines is defined as a constant is defined as 1 by 2 lambda. 2 lambda for our easy to write the circular equations for that. That's the reasons 2 lambda is given. So what I am to say is that before find out what could be the equations, you should understand the flow things, that what could be the conditions. In this case, very easily you can say that there will be the equation of the circles will be there to define these things. That's the reasons we defined is the stream functions is 1 by 2 lambda values, and if I substitute that value as y square plus y square 1 by 2 lambda, and these equations if I further simplified it, which is the equations for a circles, we can write it like this form. That's what is representing here. It is a circle of radius centered at, it is a circle radius centered at 0 and the lambda. As the lambda will vary, we will change it, the circles, different circles will get it. That's what is the solution for this. So with this, let's complete this Blackboard lectures what we have prepared by solving the 6 problems. Thank you.